The definition of the chicken game is an extreme game theory where if neither side concede, both parties face mutual destruction. To make it easy, it means winner takes it all, loser loses all. The chicken game in the memory semiconductor industry reflects a similar pattern as in theory. In 1971, of the semiconductor market, Japan outpaced the United States by selling DRAM at lower price. In the second chicken game in 2007, both South Korea and the United States employed similar strategies, offering better and cheaper DRAM, while Japan had made overspec DRAM. So the Korea and USA have successfully dominated the market. In the third game in 2010, South Korea pursued a high-end strategy, while Japan and Taiwan are facing capital shortage. Korea adopted a mass market approach. Additionally, through technological development and material advancement, more affordable and higher quantities of memory semiconductors were produced, enhancing price competitiveness and market dominance. The super cycle refers to a long-term trend of price increase over 10 to 20 years for commodities like raw materials. However, the semiconductor supercycle is somewhat different. Unlike other commodities where production is based on orders, the semiconductor industry, especially in the case of memory semiconductors, operates on a system of manufacturing first and then selling the products, chips. This leads to a cycle where price rise due to the increased demand and technological advancements. And this phenomenon is particularly observed in DRAM prices, used in devices such as PCs and smartphones. As technology and demand increase, the price for memory semiconductor, especially DRAM, tend to rise. The price increase is sustained for a period of 2 to 5 years, creating a cycle known as the memory semiconductor super cycle. Looking on ahead, based on the recent announcement, it is anticipated that three mentioned companies, SK Hynix, Samsung Electronics, and Micron, deciding on production cuts could lead a cyclical pattern in memory semiconductor industry. This cycle would involve supply reduction initiated by manufacturers, followed by inventor depletion, price stabilization, demand recovery, and further inventory reduction. According to the financial analyst, Samsung Electronics, after deciding on production cut in the first quarter, is expected to return to profitability within at least the fourth quarter in this year. Despite Samsung, the leading company in memory semiconductor, gave up its position in the recent chicken game due to the production cuts announcement. It is seen as the conclusion of this particular cycle. With the advance of AI technology and surge in demand for graphic cards, the increasing demand for memory semiconductor might lead to the possibility of another supercycle before 2025. The planar FET, which is the fundamental structure of the semiconductor, controls amplify electrical signal, as the name suggested. The planar FET has flat structure. In this structure, when a voltage is applied to the gate, a channel is formed beyond the oxide layer toward the substrate, allowing current to flow between the source and the drain. The voltage at the gate, with the threshold voltage as a reference, controls whether the current flows or not. The paper published in 1981 discussed the characteristic of the planar structure at that time. According to the paper, the characteristic of the planar structure indicates that when the doping density of semiconductor material is relatively high and the depth of the semiconductor layer is more than 1 picometer, the device's overdrive characteristics are approximately linear. Capacitance in lightly doped planar structure, capacitance is always low and nonlinear changes with gate voltage variation, a phenomenon that also applies to transconductance. Engineers of that time developed the FinFET as an alternative to the conventional PlanFET. This was driven by the need to reduce the size of transistor components to increase the integration density of semiconductor chips. With the trend toward miniaturization reaching the nanometer scale, challenges arose in controlling charge within the extremely small gauge length, leading to leakage current issues. To prevent charge leakage, either the insulating layer had to become thicker or the channel length become longer. But this would result in larger component size, defeating the purpose of miniaturization and reaching physical limits. To address this challenge, FinFET emerged. While the PlanFET structure controlled the channel on one side, FinFET with its surrounding shape controls the channel on three sides, improving control abilities. Although FinFET faced processing difficulties compared to the 2D planar structure, it overcame these challenges, ushering in the era of FinFET in the semiconductor market. The paper explains the definition and characteristic of FinFET, addressing associated issues and challenges. It initially describes the transition from planar to FinFET structure, highlighting the change in the manufacturing process and the advantage gained. The paper later discussed analog circuits utilization FinFET structure and these issues that arise. However, the limitation of FinFET technological resurfaced as the integration density increased. Higher integration implies smaller sizes, meaning the distance between fins and FinFET structure becomes closer. While chicks shape can be raised, stacking thin shapes raises the question, what happens if they're stacked too closely? Naturally, they may bend or collapse. Although various processing techniques address this, technological limitation made it increasingly difficult. This is where gate all around GAA comes into play. If FinFET controlled the gate channel through the three sides, GAA completely surrounds the channel, enabling control through four sides. Additionally, with a stacked structure, GAA improves current characteristics, although visually more complex than FinFET. GAA introduces technological challenges such as maintaining the integrated of the stacked structure and ensuring clear difference between the source and drain and metal gate. The featured paper introduced GA structure utilizing 3 nanometer technology, published by Samsung R&D Center. The paper highlights the three superior characteristics compared to the FinFET structure: 31% higher power sustainability, large width, and variable NS wide in design. As many companies are abandoning the chicken game and investing in the fabs for the next generation of semiconductor, it is expected that new material and novel process will emerge. Samsung, and the leading company in the memory semiconductor field, announced the second generation 3 nanometer process in May of this year, while TSMC considered the top layer in the foundry industry has already begun mass production of 3 nanometer process. Observing the current trend led by these companies, it is anticipated that the next generation of semiconductor will undergo changes in the materials before significant change in process. This is because the 3 nanometer process is still is early stage of precise mass production, and additionally time and sustainable capital are required for research and production. The highlight paper focused on the study of material for the next generation of components. Until now, barium titanate has been widely used as a ferroelectric material. However, the paper introduced a new material. Among them, we need to attention to the bismuth ferrite. The reason for this is that this material has a stable crystal structure, is not difficult to produce, and is more efficient than existing substance. It is considered a fully CMOS compatible material that can be used in both front end and back end aspect. As a result, achieving progress in a short period seems challenging. Consequently, from a personal perspective, it is believed that the next generation of semiconductor will likely be characterized by a shift in material.